Welcome to TensorFlow from Basics to Mastery. Some of you may have taken deep learning or machine learning from me and learned about the amazing things you can now do with deep learning and machine learning. One of the best tools you can use to implement these algorithms is TensorFlow. Learning algorithms can be quite complicated, and today, programming frameworks like TensorFlow, PyTorch, Caffe, and many others can save you a lot of time. These tools can be complicated, and what this set of courses will do is teach you how to use TensorFlow effectively. In order to teach much of these courses, I'm absolutely thrilled to introduce Laurence Moroney.
Thank you, Andrew.
He is a developer advocate at Google and has been working on Google AI and TensorFlow. Laurence has also written over 30 programming books, including 4 sci-fi novels.
Yeah, exactly. I've been busy. I really enjoy writing, but the one thing I enjoy even more is like learning and teaching AI. So, and actually, I've learned from the specializations that you mentioned, and I learned from your courses. So it's a real honor to be here with you.
Oh, thank you. I did not know that you were taking my courses as well. Thank you.
Definitely. So I was a big fan, and that's really what got me into AI was, it's actually a long story. I'd started doing AI many, many years ago, back when it was things like Prolog and Lisp and all that. But now when we've gotten more into machine learning and deep learning with neural networks, I needed a place to learn it, and I actually learned it from your courses. So it's been exciting to be actually coming full circle and now teaching it myself too.
Yeah. Thank you. I actually did not know that. So thank you for sharing that.
I caught you by surprise.
Yes.
So it's like where the industry's at right now is one of the things that like really excites me, because it's like it's really exploding, right? There's deep learning and machine learning skills are becoming ever more important and opening up whole new scenarios.
One of the strange things and exciting things about machine learning and AI is that it's no longer just a technical thing limited to the software industry, so that everyone in, or at least every industry, needs to figure this out.
Yeah, and it's exciting from a developer's perspective because there's a new paradigm, and the new paradigm to me is opening up scenarios that weren't previously possible, things that were too difficult for me to write programs for. And so, and whatever it's like, whenever a new paradigm comes and these new tools come, and you can open up new scenarios, then that opens up great new opportunities.
Yeah. And I think one of the tragic things today is, even though the whole world sees the promise and the hope of these machine learning and AI capabilities changing so many things, the world just doesn't have enough AI developers today.
Exactly. I mean, I've seen surveys of 25, 26 million software developers and like maybe 300,000 AI practitioners. So part of my personal passion is to try and turn like those 24.7 non-AI practitioners, a significant portion of them, into people who can understand AI and who can build the new and exciting things that we can't think of.
Yeah. So I think if you finish this set of courses and learn how to code in TensorFlow, hopefully that will help you do some of this exciting work and maybe become an AI developer. So in the next video, you'll hear Laurence talk about the differences between traditional programming paradigms versus the machine learning and deep learning programming paradigm. And you also hear about how to fit an X to Y data relationship, how to fit a straight line to data. So please go on to the next video.
Thank you. Coding has been the bread and butter for developers since the dawn of computing. We're used to creating applications by breaking down requirements into composable problems that can then be coded against. So, for example, if we have to write an application that figures out a stock analytic, maybe the price divided by the ratio, we can usually write code to get the values from a data source, do the calculation, and then return the result. Or, if we're writing a game, we can usually figure out the rules. For example, if the ball hits the brick, then the brick should vanish and the ball should rebound. But if the ball falls off the bottom of the screen, then maybe the player loses a life. We can represent that with this diagram. Rules and data go in, answers come out. Rules are expressed in a programming language, and data can come from a variety of sources, from local variables all the way up to databases. Machine learning rearranges this diagram where we put answers and data in, and now we get rules out. So instead of us as developers figuring out the rules, when should the brick be removed, when should the player's life end, or what's the desired analytic for any other concept, what we'll do is we can get a bunch of examples for what we want to see and then have the computer figure out the rules. Now, this is particularly valuable for problems that you can't solve by figuring the rules out for yourself. So consider this example, activity recognition. if I'm building a device that detects if somebody is, say, walking, and I have data about their speed, I might write code like this. And if they're running, well, that's a faster speed, so I could adapt my code to this. And if they're biking, well, that's not too bad either. I can adapt my code like this. But then I have to do golf recognition too. Now my concept becomes broken. But not only that, doing it by speed alone, of course, is quite naive. We walk and run at different speeds uphill and downhill, and other people walk and run at different speeds to us. So let's go back to this diagram. Ultimately, machine learning is very, very similar, but we're just flipping the axes. So instead of me trying to express the problem as rules, when often that isn't even possible, I'll have to compromise. The new paradigm is that I get lots and lots of examples, and then I have labels on those examples, and I use the data to say, this is what walking looks like, this is what running looks like, this is what biking looks like, and yes, even this is what golfing looks like. So then it becomes answers and data in, with rules being inferred by the machine. A machine learning algorithm then figures out the specific patterns in each set of data that determines the distinctiveness of each. And that's what's so powerful and exciting about this programming paradigm. It's more than just a new way of doing the same old thing. It opens up new possibilities that were infeasible to do before. So in the next few minutes, I'm going to show you the basics of creating a neural network, which is the workhorse of doing this type of pattern recognition. A neural network is just a slightly more advanced implementation of machine learning, and we call that deep learning. But fortunately, it's actually very easy to code, so we're just going to jump straight into deep learning. We'll start with a simple one, and then we'll move on to one that does computer vision in about 10 lines of code. But let's start with a very simple hello world example, so you can see just how everything hangs together. Earlier, we mentioned that machine learning is all about a computer learning the patterns that distinguish things. Like for activity recognition, it was the pattern of walking, running, and biking that could be learned from various sensors on a device. To show how that works, let's take a look at a set of numbers and see if you can determine the pattern between them. Okay, here are the numbers. There's a formula that maps x to y. Can you spot it? Take a moment. Okay, well the answer is y equals 2x minus 1. So whenever you see a y, it's twice the corresponding x minus 1. And if you figured it out for yourself, well done, but how did you do that? How would you think you could figure this out? Maybe you can see that the y increases by 2 every time the x increases by 1, so it probably looks like y equals 2x plus or minus something. And then when you saw x equals 0 and y equals minus 1, so you thought, hey, the something is a minus 1, so the answer might be y equals 2x minus 1. You probably tried that out with a couple of other values and see that it fits. Congratulations! You've just done the basics of machine learning in your head. So let's take a look at it in code now. Okay, here's our first line of code. This is written using Python and TensorFlow and an API in TensorFlow called Keras. And Keras makes it really easy to define neural networks. A neural network is basically a set of functions which can learn patterns. Don't worry if there are a lot of new concepts here. They will become clear quite quickly as you work through them. The simplest possible neural network is one that has only one neuron in it, and that's what this line of code does. In Keras, you use the word dense to define a layer of connected neurons. There's only one dense here, so there's only one layer, and there's only one unit in it, so a single neuron. Successive layers are defined in sequence, hence the word sequential. But as I've said, there's only one, so you have a single neuron. You define the shape of what's input to the neural network in the first, and in this case the only, layer, and you can see that our input shape is super simple, it's just one value. You've probably seen that for machine learning, you need to know and use a lot of math, calculus, probability, and the like. It's really good to understand that as you want to optimize your models, but the nice thing for now about TensorFlow and Keras is that a lot of that math is implemented for you in functions. There are two function roles that you should be aware of though, and these are loss functions and optimizers. This code defines them. I like to think about it this way. The neural network has no idea of the relationship between x and y, so it makes a guess. Say it guesses y equals 10x minus 10. It will then use the data that it knows about, that's the set of x's and y's that we've already seen, to measure how good or how bad its guess was. The loss function measures this, and then gives the data to the optimizer, which figures out the next guess. So the optimizer thinks about like how good or how badly the guess was done using the data from the loss function. And then the logic is that each guess should be better than the one before. As the guesses get better and better and better and accuracy approaches 100%, the term convergence is used. In this case, the loss is mean squared error, and the optimizer is SGD, which stands for stochastic gradient descent. If you want to learn more about these particular functions, as well as the other options that might be better in other scenarios, check out the TensorFlow documentation. But for now, we're just going to use these. Our next step is to represent the known data. These are the x's and the y's that you saw earlier. The np.array is using a Python library called NumPy that makes data representation, particularly in lists, much easier. So here you can see we have one list for the x's and another one for the y's. The training takes place in the fit command. Here we're asking the model to figure out how to fit the x values to the y values. The epochs equals 500 value means that it will go through the training loop 500 times. And this training loop is what we described earlier. Make a guess, measure how good or how bad the guess is with the loss function, then use the optimizer and the data to make another guess, and repeat this. When the model has finished training, it will then give you back values using the predict method. So it hasn't previously seen 10, and what do you think it will return when you pass it a 10? Now you might think it would return 19, because after all y equals 2x minus 1, and you think it should be 19. But when you try this in the workbook yourself, you'll see that it will return a value very close to 19, but not exactly 19. Now why do you think that would be? Ultimately, there are two main reasons. The first is that you trained it using very little data. There's only 6 points. Those 6 points are linear, but there's no guarantee that for every x, the relationship will be y equals 2x minus 1. There's a very high probability that y equals 19 for x equals 10, but the neural network isn't positive. So it will figure out a realistic value for y. And that's the second main reason. When using neural networks, as they try to figure out the answers for everything, they deal in probability. You'll see that a lot, and you'll have to adjust how you handle answers to fit. Keep that in mind as you work through the code. Okay, enough theory. Now let's get hands-on and write the code that we just saw, and then we can run it. So in that lesson, we just saw the basics of the new programming paradigm that comes with machine learning and deep learning, and how instead of like expressing rules in a programming language, we can start getting data and using labeled data to open up new scenarios like activity recognition. And then for a little bit of fun, we actually started doing our first piece of code. We built a super simple neural network that fit data, like X and Y data, onto a line. But that was just hello world, right, Andrew?
Yeah, so fitting a straight line seems like the hello world most basic implementation of learning algorithm, but one of the most amazing things about machine learning is that that core of the idea of fitting the X and Y relationship is what lets us do amazing things like have computers look at the picture and do activity recognition, or look at the picture and tell us, is this a dress or a pair of pants or a pair of shoes? Really hard for humans, and amazing that computers can now use this to do these things as well.
Right, like computer vision is a really hard problem to solve, right? Like as you're saying, like dress or shoes, it's like, how would I write rules for that? How would I say, you know, if this pixel, then it's a shoe, if that pixel, then it's a dress? It's really hard to do. So the labeled samples are the right way to go.
Yeah, one of the non-intuitive things about vision is that it's so easy for a person to look at you and say, oh, you're wearing a shirt. It's so hard for a computer to figure it out. And because it's so easy for humans to recognize objects, it's almost difficult to understand why this is a complicated thing for a computer to do. Yeah, what the computer has to do is look at a lot of numbers, all the pixel brightness values, say, look at all these numbers and say, oh, these numbers correspond to a black shirt. And it's amazing that with machine learning, deep learning, computers are getting really good at this.
Right. So it's like with the code that we just used in the previous lesson, as you mentioned it provides a template for everything that we can do with deep learning by designing a neural network in the layers to be able to recognize patterns like this. So maybe we can do that with clothes recognition too. What do you think?
Yeah, so in the next video, you learn how to write code to take this paradigm you've already saw in the previous video, but to now apply it to recognizing clothes from labeled data. Please go on to the next video.
In the previous lesson, you learned what the machine learning paradigm is and how you use data and labels and have a computer infer the rules between them for you. You looked at a very simple example where it figured out the relationship between two sets of numbers. Let's now take this to the next level by solving a real problem, computer vision. Computer vision is the field of having a computer understand and label what is present in an image. Consider this slide. When you look at it, you can interpret what a shirt is or what a shoe is, but how would you program for that? If an extraterrestrial who had never seen clothing walked into the room with you, how would you explain the shoes to it? It's really difficult, if not impossible to do, right? And it's the same problem with computer vision. So one way to solve that is to use lots of pictures of clothing and tell the computer what that's a picture of, and then have the computer figure out the patterns that give you the difference between a shoe and a shirt and a handbag and a coat. And that's what you're going to learn how to do in this section. Fortunately, there's a data set called Fashion MNIST, which gives us 70,000 images spread across 10 different items of clothing. These images have been scaled down to 28 by 28 pixels. Now, usually the smaller the better because the computer has less processing to do. But of course, you need to retain enough information to be sure that the features in the object can still be distinguished. And if you look at this slide, you can still tell the difference between shirts, shoes, and handbags, so this size does seem to be ideal. And it makes it great for training a neural network. The images are also in grayscale, so the amount of information is also reduced. Each pixel can be represented in values from 0 to 255, and so it's only 1 byte per pixel. With 28 by 28 pixels in an image, only 784 bytes are needed to store the entire image. Despite that, we can still see what's in the image, and in this case, it's an ankle boot, right? In the previous lesson, you learned what the machine learning paradigm is, and how you use data and labels and have a computer infer the rules between them for you. You looked at a very simple example where it figured out the relationship between two sets of numbers. Let's now take this to the next level by solving a real problem, computer vision. Computer vision is the field of having a computer understand and label what is present in an image. Consider this slide. When you look at it, you can interpret what a shirt is or what a shoe is, but how would you program for that? If an extraterrestrial who had never seen clothing walked into the room with you, how would you explain the shoes to it? It's really difficult, if not impossible to do, right? And it's the same problem with computer vision. So one way to solve that is to use lots of pictures of clothing and tell the computer what that's a picture of, and then have the computer figure out the patterns that give you the difference between a shoe and a shirt and a handbag and a coat. And that's what you're going to learn how to do in this section. Fortunately, there's a data set called Fashion MNIST, which gives us 70,000 images spread across 10 different items of clothing. These images have been scaled down to 28 by 28 pixels. Now, usually the smaller the better because the computer has less processing to do. But of course, you need to retain enough information to be sure that the features in the object can still be distinguished. And if you look at this slide, you can still tell the difference between shirts, shoes, and handbags, so this size does seem to be ideal. And it makes it great for training a neural network. The images are also in grayscale, so the amount of information is also reduced. Each pixel can be represented in values from 0 to 255, and so it's only 1 byte per pixel. With 28 by 28 pixels in an image, only 784 bytes are needed to store the entire image. Despite that, we can still see what's in the image, and in this case, it's an ankle boot, right? So what will handling this look like in code? In the previous lesson, you learned about TensorFlow and Keras and how to define a super simple neural network with them. In this lesson, you're going to use them to go a little deeper, but the overall API should look familiar. The one big difference will be in the data. The last time you had just 6 pairs of numbers so you could hard code it. This time you have to load 70,000 images off the disk, so there'll be a bit of code to handle that. Fortunately, it's still quite simple because Fashion MNIST is available as a dataset with an API call in TensorFlow. We simply declare an object of type MNIST, loading it from the Keras database, and on this object, if we call the load data method, it will return 4 lists to us. There's the training data, the training labels, the testing data, and the testing labels. Now, what are these, you might ask? Well, When building a neural network like this, it's a nice strategy to use some of your data to train the neural network and similar data that the model hasn't yet seen to test how good it is at recognizing the images. So in the FashionMNIST dataset, 60,000 of the 70,000 images are used to train the network, and then 10,000 images, one that it hasn't previously seen, can be used to test just how good or how bad it is performing. So this code will give you those sets. And then each set has data, the images themselves and labels, and that's what the image is actually of. So, for example, the training data will contain images like this one and a label that describes the image like this. While this image is an ankle boot, the label describing it is the number 9. Now, why do you think that might be? There's two main reasons. First, of course, is that computers do better with numbers than they do with text. And second, importantly, is that this is something that can help us reduce bias. If we labeled it as an ankle boot, we would be, of course, biasing towards English speakers. But with it being a numeric label, we can then refer to it in our appropriate language, be it English, Chinese, Japanese, or here, even Irish Gaelic. Okay, so now we will look at the code for the neural network definition. Remember last time we had a sequential with just one layer in it? Now we have 3 layers. The important things to look at are the first and the last layers. The last layer has 10 neurons in it because we have 10 classes of clothing in the dataset. These should always match. The first layer is a flattened layer with the input shape being 28 by 28. Now if you remember, our images are 28 by 28, so we're specifying that this is the shape that we should expect the data to be in. Flatten takes this 28 by 28 square and turns it into a simple linear array. The interesting stuff happens in the middle layer, sometimes also called a hidden layer. This has 128 neurons in it, and I'd like you to think about these as variables in a function. Maybe call them x1, x2, x3, etc. Now there exists a rule that incorporates all of these that turns the 784 values of an ankle boot into the value 9, and similar for all of the other 70,000. It's too complex a function for you to see by mapping the images yourself, but that's what a neural net does. So for example, if you then say the function was y equals w1 times x1 plus w2 times x2 plus w3 times x3 all the way up to w128 times x128, and by figuring out the values of w, then y will be 9 when you have the input value of the shoe. You'll see that it's doing something very, very similar to what we did earlier when we figured out y equals 2x minus 1. In that case, the 2 was the weight of x, so I'm saying y equals w1 times x1, etc. Now don't worry if this isn't very clear right now. Over time you will get the hang of it, seeing that it works, and there's also some tools that will allow you to peek inside to see what's going on. The important thing for now is to get the code working so you can see a classification scenario for yourself. You can also tune the neural network by adding, removing, and changing layer size to see the impact. You'll do that in the next exercise. Also, if you want to go further, check out this tutorial from Andrew on YouTube, which will clarify how dense connected layers work from the theoretical and mathematical perspective. But for now, let's get back to the code. Okay, so you just saw how to create a neural network that gives basic computer vision capabilities to recognize different items of clothing. Let's now work through a workbook that has all of the code to do that. You'll then go through this workbook yourself, and if you want, you can try some exercises. Let's start by importing TensorFlow. I'm going to get the FashionMNIST data using tf.keras.datasets. By calling the load data method, I'll get training data and labels as well as test data and labels. For more details on these, check back to the previous video. The data for a particular image is a grid of values from 0 to 255 with pixel grayscale values. Using matplotlib, I can plot these as an image to make it easier to inspect. I can also print out the raw values so we can see what they look like. Here you can see the raw values for the pixel numbers from 0 to 255, and here you can see the actual image. That was for the first image in the array. Let's take a look at the image at index 42 instead, and we can see the different pixel values and the actual graphic. Our image has values from 0 to 255, but neural networks work better with normalized data. So let's change it to between 0 and 1 simply by dividing every value by 255. In Python, you can actually divide an entire array with one line of code like this. So now we design our model. As explained earlier, there's an input layer in the shape of the data and an output layer in the shape of the classes, and one hidden layer that tries to figure out the roles between them. Now we compile the model defining the loss function and the optimizer, and the goal of these is, as before, to make a guess as to what the relationship is between the input data and the output data, measure how well or how badly it did using the loss function, use the optimizer to generate a new guess, and repeat. We can then try to fit the training images to the training labels. We'll just do it for 5 epochs to be quick. We spend about 25 seconds training it over 5 epochs, and we end up with a loss of about 0.29. That means it's pretty accurate in guessing the relationship between the images and their labels. That's not great, but considering it was done in just 25 seconds with a very basic neural network, it's not bad either. But a better measure of performance can be seen by trying the test data. These are images that the network has not yet seen. You would expect performance to be worse, but if it's much worse, you have a problem. As you can see, it's about 0.345 loss, meaning it's a little bit less accurate on the test set. It's not great either, but we know we're doing something right. Your job now is to go through the workbook, try the exercises, and see by tweaking the parameters on the neural network or changing the epochs if there's a way for you to get it above 0.71 loss accuracy on training data and 0.66 accuracy on test data. Give it a try for yourself. A question I often get at this point from programmers, in particular when experimenting with different numbers of epochs, is, how can I stop training when I reach a point that I want to be at? Why do I always have to hard code it to go for a certain number of epochs? Well, the good news is that the training loop does support callbacks. So on every epoch, you can call back to a code function, have it check the metrics, and if they're what you want to see, then you can cancel the training at that point. Let's take a look. Okay, so here's our code for training the neural network to recognize the fashion images. In particular, keep an eye on the model.fit function that executes the training loop. You can see that here. What we'll now do is write a callback in Python. Here's the code. It's implemented as a separate class, but that can be inline with your other code. It doesn't need to be in a separate file. In it, we'll implement the onEpochEnd function, which gets called by the callback whenever the epoch ends. It also sends a logs object, which contains lots of great information about the current state of training. For example, the current loss is available in the logs, so we can query it for a certain amount. For example, here I'm checking if the loss is less than 0.4 and cancelling the training if so. Now that we have our callback, let's return to the rest of the code, and there are 2 modifications that we need to make. First, we instantiate the class that we just created. We do that with this code. And then, in my model.fit, I use the callbacks parameter and pass it this instance of the class. Let's see this in action. Let's take a look at the code for callbacks and see how it works. You can see the code here. Here's the notebook with the code already written, and here's the class that we defined to handle the callback. And here's where we instantiate the callback class itself. Finally, here's where we set up the callback to be called as part of the training loop. As we begin training, note that we ask it to train for 5 epochs. Now keep an eye on the loss as it trains. We want to break when it goes below 0.4, and by the end of the first epoch, we're actually getting close already. As the second epoch begins, it has already dropped below 0.4, but the callback hasn't been hit yet. That's because we set it up for onEpochEnd. It's good practice to do this because with some data and some algorithms, the loss may vary up and down during the epoch because all of the data hasn't yet been processed. So I like to wait for the end to be sure. Now the epoch has ended and the loss is 0.3563, and we can see that the training ends even though we've only done 2 epochs. Note that we're sure we asked for 5 epochs and that we ended after 2 because the loss is below 0.4, which we checked for in the callback. It's pretty cool, right?
The fashion MNIST dataset was created by Hans-Xiao Kashifrazov and Roland Bograf, and I think it's really cool that you're already able to implement a neural network to do this fashion classification task.
And it's just amazing that like large data sets like this are readily available to students so that they can learn and make it really easy to learn. And in this case, we saw with just a few lines of code, we were able to build a DNN that allowed you to do this classification of clothing. And we got reasonable accuracy with it, but it was a little bit of a naive algorithm that we used, right? Where we're looking at every pixel in every image, but maybe there's ways that we can make it better, but maybe looking at the features of what makes a shoe and what makes a handbag a handbag. What do you think?
Yeah. So one of the ideas that will make these neural networks work much better is to use convolutional neural networks, where instead of looking at every single pixel and say, oh, that pixel has value 87, that has value 127, so is this a shoe or is this a handbag? I don't know. But instead you can look at a picture and say, oh, I see shoelaces and a sole, then it's probably a shoe. Or say, I see a handle and a rectangular bag beneath that, probably a handbag. So ConvNets hopefully will let the students do this.
Sure. So, what's really interesting about convolutions is they sound complicated, but they're actually quite straightforward, right? It's a filter that you pass over an image in the same way as if you're doing sharpening, if you've ever done image processing, and it can spot features within the image, as you've mentioned.
Yeah. And with the same paradigm of just data labels, we can let the neural network figure out for itself that it should look for shoelaces and soles or handles and bags and just learn how to detect these things by itself.
So should we see what impact that would have on Fashion MNIST?
So in the next video, you learn about convolutional neural networks and get to use it to build a much better fashion classifier.
In the previous example, you saw how you could create a neural network called a deep neural network to pattern match a set of images of fashion items to labels. In just a couple of minutes, you were able to train it to classify with a pretty high accuracy on the training set, but a little less on the test set. Now, one of the things that you would have seen when you looked at the images is that there's a lot of wasted space in each image. And while there are only 784 pixels, it would be interesting to see if there was a way that we could condense the image down to the important features that distinguish what makes it a shoe or a handbag or a shirt. And that's where convolutions come in. So what's a convolution, you might ask? Well, if you've ever done any kind of image processing, it usually involves having a filter and passing that filter over the image in order to change the underlying image. The process works a little bit like this. For every pixel, take its value and take a look at the value of its neighbors. If our filter is 3 by 3, then we can take a look at the immediate neighbor so that you have a corresponding 3 by 3 grid. Then to get the new value for the pixel, we simply multiply each neighbor by the corresponding value in the filter. So for example, in this case, our pixel has the value 192, and its upper left neighbor has the value 0. The upper left value in the filter is -1, so we'd multiply 0 by -1. Then we would do the same for the upper neighbor. Its value is 64, and the corresponding filter value is 0, so we'd multiply those out. Repeat this for each neighbor and each corresponding filter value, and would then have the new pixel be the sum of each of the neighbor values multiplied by their corresponding filter value. And that's a convolution. It's really as simple as that. The idea here is that some convolutions will change the image in such a way that certain features in the image get emphasized. So for example, if you look at this filter, then the vertical lines in the image really pop out. And with this filter, the horizontal lines pop out. Now that's a very basic introduction to what convolutions do. And when they're combined with something called pooling, they can become really powerful. Put simply, pooling is a way of compressing an image. A quick and easy way to do this is to go over the image 4 pixels at a time, i.e. the current pixel and its neighbors underneath and to the right of it. Of these 4, pick the biggest value and keep just that. So for example, you can see it here. My 16 pixels on the left are turned into the 4 pixels on the right by looking at them in 2 by 2 grids and picking the biggest value. This will preserve the features that were highlighted by the convolution while simultaneously quartering the size of the image. We have the horizontal and vertical axes. In the previous example, you saw how you could create a neural network called a deep neural network to pattern match a set of images of fashion items to labels. In just a couple of minutes, you were able to train it to classify with a pretty high accuracy on the training set, but a little less on the test set. Now, one of the things that you would have seen when you looked at the images is that there's a lot of wasted space in each image. And while there are only 784 pixels, it would be interesting to see if there was a way that we could condense the image down to the important features that distinguish what makes it a shoe or a handbag or a shirt. And that's where convolutions come in. So what's a convolution, you might ask? Well, if you've ever done any kind of image processing, it usually involves having a filter and passing that filter over the image in order to change the underlying image. The process works a little bit like this. For every pixel, take its value and take a look at the value of its neighbors. If our filter is 3 by 3, then we can take a look at the immediate neighbor so that you have a corresponding 3 by 3 grid. Then to get the new value for the pixel, we simply multiply each neighbor by the corresponding value in the filter. So for example, in this case, our pixel has the value 192, and its upper left neighbor has the value 0. The upper left value in the filter is -1, so we'd multiply 0 by -1. Then we would do the same for the upper neighbor. Its value is 64, and the corresponding filter value is 0, so we'd multiply those out. Repeat this for each neighbor and each corresponding filter value, and would then have the new pixel be the sum of each of the neighbor values multiplied by their corresponding filter value. And that's a convolution. It's really as simple as that. The idea here is that some convolutions will change the image in such a way that certain features in the image get emphasized. So for example, if you look at this filter, then the vertical lines in the image really pop out. And with this filter, the horizontal lines pop out. Now that's a very basic introduction to what convolutions do. And when they're combined with something called pooling, they can become really powerful. Put simply, pooling is a way of compressing an image. A quick and easy way to do this is to go over the image 4 pixels at a time, i.e. the current pixel and its neighbors underneath and to the right of it. Of these 4, pick the biggest value and keep just that. So for example, you can see it here. My 16 pixels on the left are turned into the 4 pixels on the right by looking at them in 2 by 2 grids and picking the biggest value. This will preserve the features that were highlighted by the convolution while simultaneously quartering the size of the image. We have the horizontal and vertical axes. So now let's take a look at convolutions and pooling in code. We don't have to do all the math for filtering and compressing. We simply define convolutional and pooling layers to do the job for us. So here's our code from the earlier example, where we defined out a neural network to have an input layer in the shape of our data, an output layer in the shape of the number of categories we're trying to define, and a hidden layer in the middle. The flatten takes our square 28 by 28 images and turns them into a one-dimensional array. To add convolutions to this, you use code like this. You'll see that the last 3 lines are the same, the flatten, the dense hidden layer with 128 neurons, and the dense output layer with 10 neurons. What's different is what has been added on top of this. Let's take a look at this line by line. Here we're specifying the first convolution. We're asking Keras to generate 64 filters for us. These filters are 3 by 3. Their activation is ReLU, which means that negative values will be thrown away. And finally, the input shape is, as before, the 28 by 28. That extra 1 just means that we're telling it we're using a single byte for color depth. As we saw before, our images are grayscale, so we just use 1 byte. Now, of course, you might wonder what the 64 filters are. It's a little beyond the scope of this class to define them, but they aren't random. They start with a set of known good filters in a similar way to the pattern fitting that you saw earlier, and the ones that work from that set are learned over time. For more details on convolutions and how they work, there's a great set of resources here. This next line of code will then create a pooling layer. It's max pooling because we're going to take the maximum value. We're saying it's a 2 by 2 pool, so for every 4 pixels, the biggest one will survive, as shown earlier. We then add another convolutional layer and another max pooling layer, so that the network can learn another set of convolutions on top of the existing one, and then again pool to reduce the size. So by the time the image gets to the flatten to go into the dense layers, it's already much smaller. It's been quartered and then quartered again, so its content has been greatly simplified. The goal being that the convolutions will filter it to the features that determine the output. A really useful method on the model is the model.summary method. This allows you to inspect the layers of the model and see the journey of the image through the convolutions. And here is the output. It's a nice table showing us the layers and some details about them, including the output shape. It's important to keep an eye on the output shape column. When you first look at this, it can be a little bit confusing and feel like a bug. After all, isn't the data 28 by 28, so why is the output 26 by 26? The key to this is remembering that the filter is a 3 by 3 filter. Consider what happens when you start scanning through an image starting on the top left. So for example, with this image of the dog on the right, you can see zoomed into the pixels at its top left corner. You can't calculate the filter for the pixel in the top left because it doesn't have any neighbors above it or to its left. In a similar fashion, the next pixel to the right won't work either because it doesn't have any neighbors above it. So logically, the first pixel that you can do calculations on is this one, because this one, of course, has all 8 neighbors that a 3 by 3 filter needs. This, when you think about it, means that you can't use a 1 pixel margin all around the image, so the output of the convolution will be 2 pixels smaller on X and 2 pixels smaller on Y. If your filter is 5 by 5 for similar reasons, your output will be 4 smaller on X and 4 smaller on Y. So that's why with a 3 by 3 filter, our output from the 28 by 28 image is now 26 by 26. We've removed that 1 pixel on X and Y in each of the borders. So next is the first of the max pooling layers. Now remember we specified it to be 2 by 2, thus turning 4 pixels into 1 and halving our X and Y. So now our output gets reduced from 26 by 26 to 13 by 13. The convolutions will then operate on that, and of course we lose the 1 pixel margin as before, so we're down to 11 by 11. Add another 2 by 2 max pooling to have this, rounding down, and we're now down to 5 by 5 images. So now our dense neural network is the same as before, but it's being fed with 5 by 5 images instead of 28 by 28 ones. But remember, it's not just one compressed 5 by 5 image instead of the original 28 by 28. There are a number of convolutions per image that we specified, in this case 64. So there are 64 new images of 5 by 5 that are being fed in. Flatten that out, and you have 25 pixels times 64, which is 1600. So you can see that the new flattened layer has 1600 elements in it, as opposed to the 784 that you had previously. This number is impacted by the parameters that you set when defining the convolutional 2D layers. Later, when you experiment, you'll see what the impact of setting what other values for the number of convolutions will be, and in particular, you can see what happens when you're feeding less than 784 overall pixels in. Training should be faster, but is there a sweet spot where it's more accurate? Well, let's switch to the workbook and we can try it out for ourselves. In the previous video, you looked at convolutions and got a glimpse for how they worked. By passing filters over an image to reduce the amount of information, they then allowed the neural network to effectively extract features that can distinguish one class of image from another. You also saw how pooling compresses the information to make it more manageable. This is a really nice way to improve our image recognition performance. Let's now look at it in action using a notebook. Here's the same neural network that you used before for loading the set of images of clothing and then classifying them. By the end of Epoch 5, you can see the loss is around 0.29, meaning your accuracy is pretty good on the training data. It took just a few seconds to train, so that's not bad. With the test data as before and as expected, the loss is a little higher, and thus the accuracy is a little lower. So now you can see the code that adds convolutions and pooling. We're going to do 2 convolutional layers, each with 64 convolutions, and each followed by a max pooling layer. You can see that we defined our convolutions to be 3 by 3 and our pools to be 2 by 2. Let's train. The first thing you'll notice is that the training is much slower. For every image, 64 convolutions are being tried, and then the image is compressed, and then another 64 convolutions, and then it's compressed again, and then it's passed through the DNN, and that's for 60,000 images that this is happening on each epoch. So it might take a few minutes instead of a few seconds. Now that it's done, you can see that the loss has improved a little. In this case, it's brought our accuracy up a bit, for both our test data and with our training data. That's pretty cool, right? Now let's take a look at the code at the bottom of the notebook. Now this is a really fun visualization of the journey of an image through the convolutions. First, I'll print out the first 100 test labels. The number 9, as we saw earlier, is a shoe or a boot. I've picked out a few instances of this where the 0th, the 23rd, and the 28th labels are all 9, so let's take a look at their journey. The Keras API gives us each convolution and each pooling and each dense, etc. as a layer. So with the Layers API, I can take a look at each layer's output, so I'll create a list of each layer's output. I can then treat each item in the layer as an individual activation model if I want to see the result of just that layer. And now, by looping through the layers, I can display the journey of the image through the first convolution, and then the first pooling, and then the second convolution, and then the second pooling. Note how the size of the image is changing by looking at the axes. If I set the convolution number to 1, we can see that it almost immediately detects the laces area as a common feature between the shoes. So for example, if I change the third image to be 1, which looks like a handbag, you'll see that it also has a bright line near the bottom that could look like the sole of the shoes, but by the time it gets through the convolutions, that's lost. And that area for the laces doesn't even show up at all, so this convolution definitely helps me separate a shoe from a handbag. And again, if I set it to 2, it appears to be trousers, but the feature that detected something that the shoes had in common fails again. Also, if I change my third image back to that for shoe, but I try a different convolution number, you'll see that for convolution 2, it didn't really find any common features. To see commonality in a different image, try images 2, 3, and 5. These all appear to be trousers. Convolutions 2 and 4 seem to detect this vertical feature as something they all have in common. If I again go to the list and find 3 labels that are the same, in this case 6, I can see what they signify. When I run it, I can see that they appear to be shirts. Convolution 4 doesn't do a whole lot, so let's try 5. And we can kind of see that the collar appears to light up in this case. Let's try convolution 1. I don't know about you, but I could play with this all day. Now see what you do when you run it for yourself. When you're done playing, try tweaking the code with these suggestions. Editing the convolutions, removing the final convolution, and adding more, etc., etc. Also, in a previous exercise, you added a callback that finished training once the loss hit a certain amount, so try to add that here. When you're done, we'll move to the next stage, and that's dealing with images that are larger and more complex than these ones, to see how convolutions can maybe detect features when they aren't always in the same place, like they would be in these tightly controlled 28 by 28 images. In the previous lessons, you saw the impact that convolutions and pooling had on your network's efficiency in learning, but a lot of that was theoretical in nature. So I thought it would be interesting to hack some code together to show how a convolution actually works. We'll also create a little pooling algorithm so you can visualize its impact. There's a notebook that you can play with too, and I'll step through that here. Here's the notebook for playing with convolutions. It does use a few Python libraries that you may not be familiar with, such as CV2. It also has matplotlib that we used before, and if you haven't used them, they're really quite intuitive for this task, and they're very, very easy to learn. So first, we'll set up our inputs, and in particular, import the misc library from SciPy. Now this is a nice shortcut for us because misc.ascent returns a nice image that we can play with, and we don't have to worry about managing our own. Matplotlib contains the code for drawing an image, and it will render it right in the browser with Colab. And here we can see the ascent image from SciPy. Next up, we'll take a copy of the image and we'll edit it with our homemade convolutions, and we'll create variables to keep track of the x and y dimensions of the image. So we can see here that it's a 512 by 512 image. So now let's create a convolution as a 3 by 3 array. We'll load it with values that are pretty good for detecting sharp edges first. And here's where we'll create the convolution. We iterate over the image, leaving a 1 pixel margin. You'll see that the loop starts at 1 and not 0, and it ends at size x minus 1 and size y minus 1. In the loop, it will then calculate the convolution value by looking at the pixel and its neighbors, and then by multiplying them out by the values determined by the filter before finally summing it all up. Let's run it. Takes just a few seconds, So when it's done, let's draw the results. And we can see that only certain features made it through the filter. I've provided a couple more filters, so let's try them. This first one is really great at spotting vertical lines. So when I run it and plot the results, we can see that the vertical lines in the image made it through. It's really cool because they're not just straight up and down, they're vertical in perspective within the perspective of the image itself. Similarly, this filter works well for horizontal lines. So when I run it and then plot the results, we can see that a lot of the horizontal lines made it through. Now let's take a look at pooling, and in this case max pooling, which takes pixels in chunks of 4 and only passes through the biggest value. I run the code and then render the output. We can see that the features of the image are maintained, but look closely at the axes and we can see that the size has been halved from the 500s to the 250s. For fun, we can try the other filter, run it, and then compare the convolution with its pooled version. And again, we can see that the features have not just been maintained, they may have also been emphasized a bit. So that's how convolutions work. Under the hood, TensorFlow is trying different filters on your image and learning which ones work when looking at the training data. As a result, when it works, you'll have greatly reduced information passing through the network, but because it isolates and identifies features, you can also get increased accuracy. Have a play with the filters in this workbook and see if you can come up with some interesting effects of your own. So there we saw that the classifier that we built for classifying fashion, like using convolutions, we're able to make it more efficient and to make it more accurate. And I thought that was really, really cool, but it's still very limited in this scenario because all of our images are 28 by 28 and the subject is actually centered. And while it's a fabulous data set for learning, it's like when we start getting into real world images and complex images that maybe we need to go a little bit further. What do you think?
Yeah, so I think it's really cool that taking the core idea of a ConvNet allows you to implement an algorithm that can find not just handbags right in the middle of the image, but anywhere in the image. So it could be carried by someone on the left or the right of a much bigger, say a 1 megapixel image. There's 1,000 by 1,000 pixels. And also for many applications, rather than using grayscale, want to use color images. And the same core ideas, but with a bigger data set, bigger images and similar labels lets you do that.
Right. So the technique that you're learning in this is really, really helping you to be able to succeed in these more real world scenarios.
So I know you've been working on a data set on horses and humans.
Yeah, so that's been a lot of fun. I've been working on a data set it's a number of images of horses and they're moving around the image and they're in different poses, and humans in the same way, and like diverse humans, male, female, different races, that kind of thing, to see if we can build a binary classifier between the two of them. But what was really interesting about this is that they're all computer generated images, but we can use them to classify real photos. I had a lot of fun with that.
Yeah. So I think that'll be a fun exercise for you to work on as well. And if you're ever wondering if these algorithms you're learning, whether this is the real stuff, the algorithms you're learning is really the real stuff that is used today in many commercial applications. For example, if you look at the way a real self-driving car today uses cameras to detect other vehicles or pedestrians to try to avoid them, they use convolutional neural networks for that part of the task, very similar to what you're learning. And in fact, in other contexts, I've heard you speak about using a convolutional neural network to take a picture.
Example,
yeah, where you can take a picture of a crop and try to tell if it has a disease coming. So that was really cool.
Oh, thank you. Thank you. That's really fun.
So in the next video, you learn how to apply convolutional neural networks to these much bigger and more complex images. Please go on to the next video.
Okay, to this point, you built an image classifier that worked using a deep neural network, and you saw how to improve its performance by adding convolutions. One limitation, though, was that it used a data set of very uniform images of clothing that were staged and framed in 28 by 28. But what happens when you use larger images and where the feature might be in different locations? For example, how about these images of horses and humans? They have different sizes and different aspect ratios. The subject can be in different locations, and in some cases there may even be multiple subjects. In addition to that, the earlier examples with the fashion data used a built-in data set. All of the data was handily split into training and test sets for you, and labels were available. In many scenarios, that's not going to be the case, and you'll have to do it for yourself. So in this lesson, we'll take a look at some of the APIs that are available to make that easier for you, in particular the image generator in TensorFlow. One feature of the image generator is that you can point it at a directory, and then the subdirectories of that will automatically generate labels for you. So for example, consider this directory structure. You have an images directory, and in that you have subdirectories for training and validation. When you put subdirectories in these for horses and humans and store the requisite images in there, the image generator can create a feeder for those images and auto-label them for you. So for example, if I point an image generator at the training directory, the labels will be horses and humans, and all of the images in each directory will be loaded and labeled accordingly. Similarly, if I point one at the validation directory, the same thing will happen. So let's take a look at this in code. The image generator class is available in keras.preprocessing.image. You can then instantiate an image generator like this. I'm going to pass rescale to it to normalize the data. You can then call the flow-from-directory method on it to get it to load images from that directory and its subdirectories. It's a common mistake that people point the generator at the subdirectory. It will fail in that circumstance. You should always point it at the directory that contains subdirectories that contain your images. The names of the subdirectories will be the labels for your images that are contained within them. So make sure that the directory you're pointing to is the correct one. You put it in the second parameter like this. Now, images might come in all shapes and sizes, and unfortunately for training a neural network, the input data all has to be the same size, so the images will need to be resized to make them consistent. The nice thing about this code is that the images are resized for you as they're loaded, so you don't need to pre-process thousands of images on your file system, but you could have done that if you wanted to. The advantage of doing it at runtime like this is that you can then experiment with different sizes without impacting your source data. While the horses and humans dataset is already in 300 by 300, when you use other datasets, they may not always be uniformly sized, so this is really useful for you. The images will be loaded for training and validation in batches, where it's more efficient than doing it one by one. Now, there's a whole science to calculating batch size that's beyond the scope of this course, but you can experiment with different sizes to see the impact on the performance by changing this parameter. Finally, there's the class mode. Now, this is a binary classifier, i.e. it picks between two different things, horses and humans, so we specify that here. Other options, in particular for more than two things, will be explored later in the course. The validation generator should be exactly the same, except of course it points at a different directory, the one containing the subdirectories containing the test images. When you go through the workbook shortly, you'll see how to download the images as a zip and then sort them into training and test subdirectories, and then put horses and human subdirectories in each. And that's just pure Python. It's not TensorFlow or any other deep learning stuff, but it's all explained for you in the notebook. So let's now take a look at the definition of the neural network that we'll use to classify horses versus humans. It's very similar to what you just used for the fashion items, but there are a few minor differences based on this data and the fact that we're using generators. So here's the code. As you can see, it's as sequential as before, with convolutions and pooling before we get to the dense layers at the bottom. But let's highlight some of the differences. First of all, you'll notice that there are three sets of convolution pooling layers at the top. This reflects the higher complexity and size of the images. Remember our 28 by 28 halved to 13 and then 5 before flattening? Well, now we have 300 by 300, so we start at 298 by 298 and then halve that, etc., until by the end we're at a 35 by 35 image. We can even add another couple of layers to this if we wanted to get to the same ballpark size as previously, but we'll keep it at 3 for now. Another thing to pay attention to is the input shape. We resized our images to be 300 by 300 as they were loaded, but they're also color images, so there are 3 bytes per pixel. 1 byte for the red, 1 for the green, and 1 for the blue channel. And that's a common 24-bit color pattern. And if you're paying really close attention, you can see that the output layer has also changed. Remember before when you created the output layer, you had 1 neuron per class, but now there's only 1 neuron for 2 classes. And that's because we're using a different activation function. where sigmoid is great for binary classification, where one class will tend towards 0 and the other class tending towards 1. You could use 2 neurons here if you want and the same softmax function as before, but for binary this is a bit more efficient. If you want, you can experiment with the workbook and give it a try for yourself. Now if we take a look at our model summary, we can see the journey of the image data through the convolutions. The 300 by 300 becomes 298 by 298 after the 3 by 3 filter. It gets pulled to 149 by 149, which in turn gets reduced to 73 by 73 after the filter. That then gets pulled to 35 by 35. This will then get flattened, so 64 convolutions that are 35 squared in shape will get fed into the DNN. And if you multiply 35 by 35 by 64, you get 78,400, and that's the shape of the data once it comes out of the convolutions. If we had just fed raw 300 by 300 images without the convolutions, that would be over 900,000 values. So we've already reduced it quite a bit. Okay, we'll now compile the model, and as always we have a loss function and an optimizer. When classifying the 10 items of fashion, you might remember that your loss function was a categorical cross-entropy. But because we're doing a binary choice here, let's pick a binary cross-entropy instead. Also earlier we used an atom optimizer. Now you could do that again, but I thought it would be fun to use the RMS prop, where you can adjust the learning rate to experiment with performance. To understand learning rate and how all that fits together, check out this great video from deeplearning.ai that goes into it in a lot more detail. For now, I'm not going to go into the details in this course. Okay, next up is the training. Now this looks a little different than before when you called model.fit, because now you call model.fit generator. And that's because we're using a generator instead of datasets. Remember the image generator from earlier? Let's look at each parameter in detail. The first parameter is the training generator that you set up earlier. This streams the images from the training directory. Remember the batch size you used when you created it? It was 20. That's important in the next step. There are 1,024 images in the training directory, so we're loading them in 128 at a time. So in order to load them all, we need to do 8 batches. So we set the steps per epoch to cover that. Here we just set the number of epochs to train for. This is a bit more complex, so let's use, say, 15 epochs in this case. And now we specify the validation set that comes from the validation generator that we also created earlier. It had 256 images, and we wanted to handle them in batches of 32, so we will do 8 steps. And the verbose parameter specifies how much to display while training is going on. With verbose set to 2, we'll get a little less animation, hiding the epoch progress. Once the model is trained, you will of course want to do some prediction on the model. And here's the code to do that. Let's look at it piece by piece. So these parts are specific to Colab. They are what give you the button that you can press to pick one or more images to upload. The image paths then get loaded into this list called uploaded. The loop then iterates through all of the images in that collection, and you can load an image and prepare it to input into the model with this code. Take note to ensure that the dimensions match the input dimensions that you specified when designing the model. You can then call model.predict, passing it the details, and it will return an array of classes. In the case of binary classification, this will only contain one item with a value close to 0 for one class and close to 1 for the other. Later in this course, you'll see multi-class classification with softmax, where you get a list of values with one value for the probability of each class and all of the probabilities adding up to 1. Okay. So you've just seen how to get started with creating a neural network in Keras that uses the image generator to automatically load and label your files based on their subdirectories. Now let's see how we can use that to build a horses or humans classifier with a convolutional neural network. This is the first notebook you can try. To start, you'll download the zip file containing the horses and humans data. Once that's done, you can unzip it to the temp directory on this virtual machine. The zip file contained 2 folders, one called filtered horses and one called filtered humans. When it was unzipped, these were created for you. So we'll just point a couple of variables at them, and then we can explore the files by printing out some of the file names. Now these could be used to generate labels, but we won't need that if we use the Keras generator. If you wanted to use this data without one, the file names will have the labels in them, of course though. We'll print out the number of images that we have to work with, and there's a little over 1,000 of them. And now we can display a few random images from the dataset. Here we can see 8 horses and 8 humans. An interesting aspect of this dataset is that all of the images are computer generated. I've rendered them to be as photoreal as possible, but they'll be actually used to classify real pictures of horses and people. And here's a few more images just to show some of the diversity. Let's start building the model. First we'll import TensorFlow, and now we'll build the layers. We have quite a few convolutions here because our source images are quite large at 300 by 300. Later we can explore the impact of reducing their size and needing less convolutions. We can print the summary of the layers, and here we can see by the time we reach the dense network, the convolutions are down to 7 by 7. Okay, next up we'll compile our network. It's using binary cross-entropy as the loss, binary because we're using just 2 classes, and the optimizer is an RMS prop that allows us to tweak the learning rate. Don't worry if you don't fully understand these yet. There are links out to content about them where you can learn more. Next up is where we use the image data generator. We instantiate it and rescale our images to 1/255, which then normalizes their values. We then point it at the main directory where we see the unzipped files. We can see that it finds all of the images and has assigned them to 2 classes because there were 2 subdirectories. We'll now train the neural network for 15 epochs. It'll take about 2 minutes. Each epoch is loading the data, calculating the convolutions, and then trying to match convolutions to labels. As you can see, the accuracy mostly increases, but it will occasionally dip, showing the gradient descent of the learning actually in action. It's always a good idea to keep an eye on fluctuations in this figure, and if they're too wild, you can adjust the learning rate. Remember the parameter to RMS prop when you compile the model. That's where you tweak it. It's also going pretty fast because right here I'm training it on a GPU machine. By the time we get to epoch 15, we can see that our accuracy is about 0.9981, which is really good. But remember, that's only based on the data that the network has already seen during training, which is only about 1,000 images, so don't get lulled into a false sense of security. Let's have a bit of fun with the model now and see if we can predict the class for new images that it hasn't previously seen. Let's go to Pixabay and see what we can find. I'll search for horses, and there's lots of horses, so let's pick this one. It's a white horse running in the snow. I'm going to download it to my file system, and now I'm going to go back to the notebook, and I'm going to upload the image from my file system, and we'll see that it gets uploaded, and it's classified as a horse. So let's try another one, like this one here, which I'll then upload to the notebook, and we'll see that it's also classified as a horse. I'll now go back to Pixabay and search for a person, and pick this image of a girl sitting on a bench. I'll download it to my file system, upload it to the neural network, and we can see that this is also correctly classified as a human. Let's do one more. I'll go back to the list of results on Pixabay and pick this image of a girl. As before, I'll download it to my file system, and I'll upload it to the neural network, and we'll also see that it still detects a human in the image. Now, one other thing that I can do with this script is upload multiple files and have it classify all of them at once. And here we can see all of the classifications. We have 4 out of 4 correct. This notebook also includes some visualizations of the image as it passes through the convolutions. You can give it a try with this script. Here you can see where a human image was convolved and features such as the legs really lit up. And if I run it again, we can see another human with similar features. Also, the hair is very distinctive. Have a play with it for yourself and see what you discover. So there we saw a convolutional neural network create a classifier to horses or humans using a set of about 1,000 images. The 4 images we tested all worked, but that's not really scalable. In the next video, we'll see how we can add a validation set to the training and have it automatically measure the accuracy of the validation set too. In the previous video, you saw how to build a convolutional neural network that classified horses against humans. When you were done, you then did a few tests using images that you downloaded from the web. In this video, you'll see how you can build validation into the training loop by specifying a set of validation images and then have TensorFlow do the heavy lifting of measuring its effectiveness with that set. As before, we'll download the dataset, but now we'll also download the separate validation dataset. We'll unzip into two separate folders, one for training and one for validation. We'll create some variables to point at our training and validation subdirectories, and we can check out the file names. Remember that the file names may not always be reliable for labels. For example, here the validation horse labels aren't named as such, while the human ones are. We can also do a quick check on whether we got all the data. And it looks good, so we think we can proceed. We can display some of the training images as we did before. And, let's just go straight to our model. Here we can import TensorFlow, and here we define the layers in our model. It's exactly the same as last time. We'll then print the summary of our model, and you can see that it hasn't changed either. And then we'll compile the model with the same parameters as before. Now here's where we can make some changes. As well as an image generator for the training data, we now create a second one for the validation data. It's pretty much the same flow. We create a validation generator as an instance of image generator, rescale it to normalize, and then point it at the validation directory. When we run it, we see that it picks up the images and the classes from that directory. So now let's train the network. Note the extra parameters to let it know about the validation data. Now, at the end of every epoch, as well as reporting the loss and accuracy on the training, it also checks the validation set to give us loss and accuracy there. And as the epochs progress, you should see them steadily increasing, with the validation accuracy being slightly less than the training. It should just take about another 2 minutes. Okay, now that we've reached epoch 15, we can see that our accuracy is about 97% on the training data and about 85% on the validation set. And this is as expected. The validation set is data that the neural network hasn't previously seen, so you would expect it to perform a little worse on it. But let's try some more images, starting with this white horse. And we can see that it was misclassified as a human. Okay, let's try this really cute one. And we can see that that's correctly classified as a horse. Okay, let's try some people. Let's try this woman in a blue dress. This is a really interesting picture because she has her back turned and her legs are obscured by the dress, but she's correctly classified as a human. Okay, here's our tricky one. To our eyes, she's human, but will the wings confuse the neural network? And they do. She's mistaken for a horse. And it's kind of understandable though, particularly as the training set has a lot of white horses against a grassy background. How about this one? It has both a horse and a human in it. But it gets classified as a horse. And we can see the dominant features in the image are the horse, so it's not really surprising. Also, there are many white horses in the training set, so it might be matching on them. Okay, one last one. I couldn't resist this image as it's so adorable. And thankfully it's classified as a horse. So now we saw the training with a validation set, and we could get a good estimate for the accuracy of the classifier by looking at the results with a validation set. Using these results and understanding where and why some inferences fail can help you understand how to modify your training data to prevent errors like that. But let's switch gears in the next video, and we'll take a look at the impact of compacting your data to make training quicker. The images in the horses or humans dataset are all 300 by 300 pixels, so we had quite a few convolutional layers to reduce the images down to condensed features. Now this of course can slow down the training. So let's take a look at what would happen if we change it to 150 by 150 for the images to have a quarter of the overall data and to see what the impact would be. We'll start, as before, by downloading and unzipping the training and test sets. Then we'll point some variables at the training and test sets before setting up the model. First, we'll import TensorFlow, and now we'll define the layers for the model. Note that we've changed the input shape to be 150 by 150, and we've removed the fourth and fifth convolutional max pool combinations. Our model summary now shows the layers starting with the 148 by 148 that was the result of convolving the 150 by 150. And we'll see that at the end we end up with a 17 by 17 by the time we're through all of the convolutions and pooling. We'll compile our model as before, and we'll create our generators as before, but note that the target size has now changed to 150 by 150. Now we can begin the training, and we can see that after the first epoch that the training is fast, and accuracy and validation aren't too bad either. The training continues and both accuracy values will tick up. Often you'll see accuracy values that are really high, like 1.000, which is likely a sign that you're overfitting. We reach the end and have really high accuracy on the test data, about 0.99, which is much too high. The validation set is about 0.84, which is pretty good, but let's put it to the test with some real images. Let's start with this image of the girl and the horse. It still classifies as a horse. And next, let's take a look at this cool horsey. And who is still correctly categorized. These cuties are also correctly categorized. But this one is still wrongly categorized. But the most interesting, I think, is this woman. When we used 300 by 300 before and more convolutions, she was correctly classified, but now she isn't. And this is a great example of the importance of measuring your training data against a large validation set, inspecting where it got it wrong, and seeing what you can do to fix it. Using this smaller set is much cheaper to train, but then errors like this woman with her back turned and her legs obscured by the dress will happen, because we don't have that data in the training set. And that's a nice hint about how to edit your data set for the best effect in training.
Congratulations on coming to the end of this first course. And wow, you've come a long way.
Yeah, I mean, we've looked at with the students, we've looked at how to use TensorFlow all the way from the beginning with doing something like fitting a straight line to then recognizing fashion items.
And it was really cool. It was like 3 lines of code to do a really complicated task like that.
And isn't it amazing, computer vision in 3 lines like that? And then we improved that by adding convolutions.
And we called it an improvement, but that means now 4 lines of code to define 2 conv layers and 2 max pool layers. And then a tool like TensorFlow take care of a lot of the rest.
Right. And then we looked at going beyond the simple images to bigger and colored images. And we didn't even add any lines of code for that, right? It was just changing the shape of the data coming in.
Yeah. So by learning a programming framework like this, you can write very complicated programs with just a few lines of code, and this helps people save a lot of time. But there's still a lot more to learn.
Oh, there is. And some of the things that we'd love to explore are things such as when you have very small data sets, that can lead to an error called overfitting. So we'll explore some techniques and tools that we can use to avoid that.
Yeah. And transfer learning, if you can download someone else's, say, TensorFlow model and use that for your own problem, even though it was trained on a totally different data set. TensorFlow has tools to let you do that efficiently as well.
Absolutely. And one of the things that a lot of AI practitioners love to be involved in is there's online competitions where places like Kaggle provide a data set, and they ask you to build a classifier around that data set. And we're going to explore some of the skills that you can use to take part in those competitions.
Cool. So congratulations again on coming to the end of the first course, and there's still all these amazing things to learn about TensorFlow. So please go on to the next course.